Hello, welcome to DC Electrical Power Basics, part of our product knowledge series. In this lesson, we're going to cover foundational concepts of electrical power with a focus on DC, which stands for direct current. DC power is what runs all of our electric RC cars, planes, our model railroad, slot cars, and this will help you with your customers. By the end of this video, you'll understand what voltage, current, resistance, and watts actually mean. And more importantly, you'll be able to use that knowledge to help a customer figure out why something isn't working the way it should. So don't worry if you've never studied electricity before. I'm not an engineer, but we're going to keep this practical and use some everyday comparisons to make these concepts as easy as possible. Now, before we get into measurements, let's talk about what electricity is at a basic level. There are three things you need to understand: equalization, a complete circuit, and the load. First, equalization. At its core, electricity is about energy trying to find balance. Everything in nature wants to equalize. Water flows until pressures are equal on both sides. Heat transfers from warm to cold until they are stabilized. Electricity works the same way. Inside every power source, a battery, power supply, whatever it might be, there is a difference in energy between 2 points. We call one side the negative and the other side the positive. The negative end has an excess of electrons, and those electrons want to move toward the positive end to balance things out. That movement of electrons through a conductor is what we call an electrical circuit. Now, a complete electrical circuit, for that flow to happen, there needs to be a complete path, a closed loop from the negative all the way back to the positive. We call that a circuit. If there's any break in that circuit, a disconnected wire, a switch that's been turned off, a blown fuse, a corroded connector, the flow stops completely. Just like water in a pipe, if there's a break or a blockage anywhere along the line, nothing reaches the other end. That's actually one of the most common things you'll be troubleshooting. A customer's model isn't working, and the answer is simply that somewhere in the circuit there's a break or a disconnection. Third is the load. The components along the circuit that actually use the energy flow are called the load. Anything that converts electrical energy into something useful, motion, light, or heat, is a load. A motor is a load. An LED or heating element would also be a load. In our hobby world, the receiver, servos, speed controller are all part of the load. The load is what the whole circuit exists to power. Understanding what's in the load will help you diagnose what might be going wrong. We're going to use water as an analogy throughout this lesson because it simplifies abstract electrical concepts and makes them easier to follow. Now, the analogy isn't perfect, but it's pretty close. On this slide, you can see all four of the measurements we'll be covering, mapped directly to their water equivalents. If you imagine a garden hose connected to a water tap with a water wheel at the end, the water flowing through that hose is a lot like electricity flowing through a wire. So, voltage is energy potential. In our water system, voltage is the pressure at the tap. The higher the voltage, the more push behind the electricity, or push for the water to flow. Turn up the pressure and more water moves. Same with voltage. The current is flow rate, measured in amps. In water terms, it'd be gallons per minute. Current tells you how much electricity is flowing or moving through the circuit at any given moment. Resistance is the restrictions, measured in ohms. Think of a narrow section of the pipe or a kink in the hose. Resistance is anything that opposes the flow. And importantly, every load in your circuit, every motor, every LED adds resistance. That's how they work. And watts is the power output, the results of all three of the others working together. In the water analogy, watts are like the horsepower generated by the water wheel at the end of the system. More pressure, more flow, more output. Side note, 1 horsepower is equal to about 735 watts. So if you keep this water model in mind, the tap or the power, the water source, the pipe or the hose, and then the water wheel on the other end. I suppose you could use a sprinkler too. So keep that in mind as we go a bit deeper on these things. Before we get really deeper on voltage, current, and resistance, we're going to take a brief moment to talk about AC versus DC, because both will come up when your customers are setting up their systems, and understanding the difference will help you support the whole picture. So where DC stands for direct current, the voltage is constant and steady. The electrons flow in one direction only, from negative to positive, without any fluctuation. If you were to plot DC on a graph with 0 volts or neutral, you'd see a positive, perfectly flat straight line. DC is what standard motor, brush motors, receivers, speed controllers, and all of our electronics need to run properly. It's the output of every battery and a DC power supply, as well as an electronic speed control powering a brush motor. AC stands for alternating current. The voltage of AC cycles continuously between positive and negative output. It doesn't flow in one direction of just positive. It's moving from positive to negative to positive to negative, and it oscillates back and forth. So if you plotted that out on a graph, what you'd see is a smooth S-shaped wave called a sine wave. If you had an oscilloscope, that's what you would see, and it'd be going from positive to negative, sweeping up into the positive, back through to 0, down to negative, back in the center, and over and over and over. And it plots out as a sine wave. In North America, that cycle happens every 60 seconds. So 0 to positive, 0, negative, back to 0. That happens in 60 times every second. And that rate is called frequency. It's measured in hertz. So that's 60 hertz. And a standard incandescent light bulb is not actually on solidly because it's powered by AC. It's technically flashing 120 times every second, once for the full positive, once for the full negative, and then back. And so it's flashing 120 times every single second, but your eye can't detect it at that speed, so it looks constant, but it's not. And AC is what's coming out of the wall. Our chargers, power supplies, and a lot of our tools, they run on this AC power, but then they convert it to DC in some fashion or another before we use it in our models. There's certainly a lot more to understand about AC power, but for our purposes, this little bit is all we need for right now. So now let's go deeper into the measurements, starting with voltage, measured in volts, written with a capital V. Volts is the potential energy difference between the negative and the positive of a power source. It's the pressure behind the electricity, or the potential for the electrons to move from the negative terminal to the positive terminal. Higher voltage means more push, more electrons or more energy available to do that work. A lower voltage means less pressure, less energy. The voltage of your power source needs to match the device, what the device is designed for. Too low, and the device might not work at all, or it might run sluggishly. Too high, and you risk damaging the electronic components. Take a look at these common voltages on the screen. You'll recognize most of these from products on our shelves. A standard alkaline battery, AA, it puts out 1.5 volts. A rechargeable nickel metal hydride cell is 1.2 volts. LiPo batteries, the packs used in most RC models currently, output 3.7 volts per individual cell. So for RC cars and planes, you'll often see 2S, 3S, or 4S LiPo packs. The S stands for cells in a series. A 2S pack has two cells connected together to give you 7.4 volts. Because you have 3.7, 3.7, 3.7 times 2 is 7.4 volts. A 3S pack has 3 cells. And 3.7 times 3 is 11.1 volts. The more cells in a series, the higher the voltage, the more performance, the more energy potential. Now, there is more info on this in our LiPo battery basics lesson, which will come soon. For model railroads, a DC power supply typically runs 12 to 18 volts. They're actually variable. That's the standard for HO and N scale trains. When a customer tells you that their model won't turn on, the first thing to check is the power. What is powering it? Is the voltage correct for the model? Is the battery even charged? Voltage is typically everything. And then current, which is measured in amps, short for amperes. You'll also see milliamps, which is abbreviated with the lowercase m and a capital A. 1 amp equals 1,000 milliamps, just like 1 meter is the same as 1,000 millimeters. So if voltage is the pressure, current is the flow. It's how much electricity is actually moving through the circuit at any given moment. In the water analogy, think gallons per minute. Current represents the actual quantity of electrons moving through the circuit. More electrons moving per second means more current, more amps. Now here's an important concept. Different devices draw different amounts of current. The keyword draw, the word draw here is key. A device doesn't consume the voltage you give it. It draws the current it needs from the source, and a small LED might only draw a few milliamps. A motor under a heavy load might draw 20, 40, even 60 amps. So look at these examples on the screen. Notice the huge range here. A small servo draws maybe 100 to 500 milliamps in normal use, where a 10 scale RC car motor at full throttle might draw 20 all the way up to 60 amps. That's up to a 600 to 1 difference between the servo and the motor. And both are very common in the models we carry. This matters a lot for wiring and connectors. Every wire and connector has a current rating. If you think of like the size of the pipe or hose that is flowing. And so the maximum amount of current that it can safely carry. If you exceed that rating and the wire heats up, the insulation can melt, and in worst case scenario, you can destroy electronics or even start a fire. When a customer asks why their motor wires are getting hot or why their connector melted, you are almost certainly looking at a current problem. Either the wire gauge is too small for the application or the connector isn't rated for the amps being drawn. Battery capacity is also measured using current. The numbers represent how many amp hours or milliamp hours, lowercase m, capital A, lowercase h, uh, milliamp hours of energy a battery stores. You'll see ratings like 2200 milliamp hours or 5000 milliamp hours on LiPo packs. So if a 1 amp hour or 1000 milliamp hour battery had a 1 amp load on it, it would supply power to that load for 1 hour. And a 2200 milliamp hour pack can deliver 2200 milliamps of current on a 2.2 amp load for 1 hour before it's depleted. If you double the load to 4.4 amps, you'll have the runtime to 30 minutes. Next is resistance, which is measured in ohms. This is represented by the Greek letter omega. It is the opposition to current flow in a circuit. In the water analogy, resistance is like the restriction in the pipe or a narrow section, a clog, or a partially closed valve. It slows things down. Now, here's something that trips people up. Resistance isn't only a bad thing. The load in a circuit, the components that actually use the energy, are themselves a source of resistance. A motor is resistance. So is an LED or a heating element. They work by opposing the current flow and converting that energy into something useful: motion, light, or heat. The problem comes when you have unwanted resistance. A bad connection, a corroded terminal, a wire that's too thin for the job. That kind of resistance doesn't do useful work. It just wastes energy as heat. This brings us to Ohm's Law. The foundational relationship between voltage, current, and resistance. Now, you don't need to run this math in your head on the shop floor. What matters is understanding this relationship. Ohm's law states voltage equals current multiplied by resistance. V equals I times R. What that means practically: voltage, current, and resistance are always connected. Change one and the others change too. For example, if resistance increases in a circuit, say because of a corroded connection, the current drops, which means the motor gets less power and runs slower. If voltage drop, current drops too, and performance suffers. Think about it like our water systems. If you start closing a valve in the pipe, increasing resistance, less water flows, even if the pressure at the source hasn't changed. When you're helping a customer diagnose a slow or underperforming model, Ohm's law is your mental framework. Something changed in the triangle. Voltage dropped, resistance increased, or current is being limited somewhere. Final is watts, which measures the power, the rate at which electrical energy is actually being used or produced. This is the measurement of the output or the reaction. The formula is simple. Watts equals volts multiplied by amps. P equals V times I. If you have a motor running at 7.4 volts and drawing 10 amps, it is consuming 74 watts. If you push it harder and it draws 20 amps, you're now at 148 watts. That extra 74 watts shows up as more speed, more torque, and more heat in the system. In our water analogy, watts are like the horsepower generated by the water wheel at the end of the system. More pressure and more flow both contribute to more power output. If you look at these numbers on the screen, a small HO scale locomotive with lights draws maybe 6 watts. A 110 scale RC car at full throttle might pull 444 watts. Both are DC, both have motors, but they're operating within completely different power ranges. So why does this matter for the customers? Two reasons. First, power supplies and batteries must be rated for the load they're going to support. If a customer buys a model railroad power supply rated at 30 watts and then tries to run a large layout that draws 50 watts, the supply will overheat, shut down, maybe even fail. The wattage rating is a ceiling, it's not a suggestion. Second, heat is an indicator. If something is running hot, a wire, a motor, a speed controller, it's losing energy as heat instead of using it productively. That heat tells you something is wrong. Too much resistance, too much current, or a component that's undersized for the job. So now that we understand what voltage, current, resistance, and watts mean, let's look at the DC power sources your customers will actually be using. Alkaline and nickel metal hydride batteries, standard AA, AAA cells, Cs or Ds, they output 1.2 to 1.5 volts per cell. They're inexpensive and widely available. Nickel metal hydrides are rechargeable. You'll see these in transmitters and small entry-level models or toys. LiPo batteries, or lithium polymer batteries, are the powerhouse of choice for performance RC. They're lightweight and they have a high energy density and can deliver some serious current. Each cell outputs 3.7 volts, and packs are configured in series 2S, 3S, 4S, 6S, whatever, to reach the voltage the model needs. Two critical rules for LiPo batteries: always use a proper LiPo charger and never fully discharge them. Over discharging a LiPo damages it permanently and can create a safety hazard. For model railroads, customers use a DC power supply, a wall-powered unit that converts AC from the outlet to a steady DC. These typically output 12 to 18 volts and are rated for a specific wattage. The power supply is the backbone of the train layout. An ESC, or electronic speed controller, sits between your battery and your motor in an RC vehicle. The battery providing, say, 11.1 volts. The ESC takes that voltage and controls how much power reaches the motor based on the throttle signal it's receiving from the receiver. Most ESCs also include a BEC, or a battery eliminator circuit, which steps the voltage down to 5 or 6 volts to safely power the receiver and the servos. A DCC decoder is the model railroad equivalent of an ESC. DCC stands for Digital Command Control. The decoder is installed inside the locomotive and receives digital commands through the track. It controls motor speed, direction, lights, and sometimes sound, all independently. The track carries the voltage, typically 12 to 18 volts of power and signal, and the decoder interprets it. And then we've also got standalone BECs, or a universal BEC. It's a voltage step-down device for RC systems that don't have a BEC built into the ESC. And it ensures, sensitive electronics never see more voltage than they're designed for. They can also power high voltage servos or accessories that are different than the receiver needs. So, and so let's bring it all together. On the screen, you'll see a quick reference. You can keep this handy and print it off when you're helping your customers. V is voltage, or volts. That's the pressure. I is current, or amps. It's the flow. R is resistance, ohms, or the opposition. P is power, or watts. It's the output. Ohm's law links the first three. Voltage equals current times resistance. Change any one of them and the others shift. And then the power formula. Watts equals volts times amps. That tells you how much energy is being consumed at any moment. At the bottom, you'll see the most common troubleshooting clues. It won't turn on. Check the supply voltage first. Motor running slow or weak. Suspect low voltage or high resistance in the circuit. Something getting hot. That's current problem. too many amps for the wire, the connector, or the component. And here are your 5 final key takeaways from this lesson. 1. Voltage is the push of power. Current is the flow of that power. Resistance is the obstacle in the way of that power. 2. They're always connected. Ohm's Law. Change one and you affect the others. 3. Watts tells you total power. Your power supply and battery must be rated to support and handle that. 4. LiPo, nickel metal hydride, DC power supplies, ESCs, and DCC decoders are all DC sources, each designed for a specific job and a specific application. 5. When a customer has a problem, your first 3 checks are voltage, connection quality, and heat. Those 3 cover the majority of common issues. Thanks for watching. If you have any questions, check in with your trainer or visit the Product Knowledge Library, and we'll see you in the next lesson. Thanks. Have fun.